welcome back in our channel. Today we will have applied example about the constant coefficient homogeneous linear second order differential equations. We have pure math and applied math. Here is an example. The right hand side is 0, so the characteristic equation is lambda square plus 25 equals 0. Here the roots are complex roots with I, and our solution will be on this form. Y equals C1 e to the power ax cosine bx plus C2 e to the power x sine bx. Here's our solution to this example. Now we have applied math physics, the pendulum. Here is our system. This is roof or supporter or ceiling, and here is theta, the same. This one as this one. And here is the bob of the pendulum. So the given data for this system that L, the length L, is massless. The weight of L is 0. And air resistance also 0. Tension is neglected. So the force here, the tangential component will be mg sine theta. And the radial force mg cosine theta. Theta is the angular displacement, and the part d theta over d times angular velocity. And this is the angular acceleration. This is the Newton's second law of motion. Force equal ma. And here is our force, because our displacement will be this way. So we put minus sign because the force against our direction. This is positive direction. And the force acting on the bob coming the opposite direction. So this is why we put minus. We divide on this is the m is cancelled, and we divide both sides of the equation by L, and we got this equation. If you remember in the first video of our series, we talk about non-linear differential equation, and we said if there is special function, sine theta or e to the sine x or e to the x or cosine ln, also of course beside many other forms like multiplication of the partial with the variable itself, like dy multiplied by y or y to the power square, this will be nonlinear. This equation is hard to solve because of the sine theta. So what we need approximation. We take theta small, maybe less than 15 degrees. So in this range, theta will be equal or approximately equal to the sine theta. I mean the sine and theta in this from 0 up to 15 or 14, it's almost close or the same. So we put, instead of sine theta, theta here. just approximation to make the equation linear, because it's very hard to solve it with sine theta, and we need software to solve that, like Mathematica or MATLAB or another software. Here is our equation. We find the roots. Lambda 1 equal plus I g over L. Lambda 2 equal minus I g over L. And the solution to this equation is theta of t, this one. This is the angular frequency, the omega, which equal 2 by f. And here is, we put, instead of g over L, we put omega. Remember, we have this relation, e to the power I alpha equal cosine alpha plus I sine alpha. Therefore, equation 1 becomes, and we factor cosine omega t, so we got C1 plus C2, and here's C1 minus C2, and they are another constant. We put A for C1 plus C2 and B for C1 minus C2. To find the constant A and B, we use the initial condition. At t equals 0, when we release the pendulum, theta was theta naught, and the velocity is 0 because we were holding the pump. And then we derive equation 2 to find d theta over dt at t equal 0. So we got this relation. Now we put the velocity 0 to find the constant A and B. And here, theta of t equal theta naught cosine omega t. Or this is the same. So this is our final solution for this system. We need to know that oscillation means the swing of the pendulum back and forth. We call it oscillation. The frequency and the number of oscillations completed in 1 second. The period time, the period t, the time it takes the pendulum to complete 1 cycle. Like from A, here this is point A, this is B, this is C. So the frequency, the time it takes the pendulum to complete 1 cycle from A to B to C and back again to B and A. We call it the period. Thank you for watching my channel, and see you in the next video for another application of constant coefficient first order linear differential, second order differential equation.